Motor control systems using solid-state devices like these AC inverters are reliable and versatile. Most inverters will run for years with almost no maintenance, and production changes can usually be accommodated by altering a few settings. And if things do go wrong, systems that use inverters are often easy to troubleshoot. Most inverters can help you identify the source of the problem so you can get the system back online quickly. To maintain inverter systems effectively, you need a fundamental understanding of what inverters do, how they work, and what common problems arise during their operation. Let's begin by looking at what inverters do and how they work. AC inverters control the speed of three-phase motors, and they control torque, the rotary force a motor produces. Since torque and speed determine the power a motor produces, inverters are also able to regulate that power by adjusting speed when the torque varies, or by adjusting torque when the speed varies. To understand how inverters control speed, torque, and power, let's look at a typical three-phase induction motor. When current is applied to the stator, it creates positive and negative magnetic fields that revolve through the stator. The rate at which these magnetic fields revolve depends upon the frequency of the applied current. The lower the frequency, the slower the magnetic fields revolve. The magnetic strength of the fields depends on the voltage applied at a particular frequency. The higher the voltage, the stronger the field. Inverters control motors by adjusting both the frequency and the voltage. These adjustments cannot be made easily without an inverter. Electromechanical methods can be used to reduce the voltage applied at startup, but the transition to full voltage occurs in large steps that may shock the motor or load and may disturb the electrical system. And since changing the voltage without changing the frequency will overheat the windings, reduced voltage can be applied for only a few seconds at most. Frequent startups may damage the motor. By contrast, this torque controller, or soft starter as it's sometimes called, gradually raises voltage in a nearly stepless ramp. This allows the motor to reach full speed and torque very smoothly, and the startup can be repeated frequently without damage to the motor. These inverters can maintain reduced voltage and frequency indefinitely, and they can also provide control of much more complicated operations, such as maintaining speed and torque when loads vary unpredictably, providing precision control of speed when necessary, and regulating the power output of a motor. Typically, this type of inverter has a microprocessor through which the user can control all the different functions by entering instructions from a keypad or a control panel. Many inverters can also be controlled by standard mechanical and electronic field devices such as limit switches, current and voltage sensors, tachometers, and photosensors. And since an inverter's operation may have to be integrated with other equipment and processes, many inverters can be controlled by an outside computer. All inverters have three main sections that together produce the adjustable frequency and voltage required by the motor. The first section, the converter or front end, changes all three phases of the incoming alternating current, AC, into direct current, DC. The converter section uses solid-state rectifiers which permit current to flow in one direction only. Separate banks of rectifiers clip the AC wave in half. This creates pulses of positive and negative DC current. The second section is called the DC filter or DC link section. It filters the DC current, smoothing out the pulses with inductors or capacitors, and depending on the type of controller, alters the voltage. The third section, the inverter or switching section, uses the positive DC pulses to simulate the rising current of an AC sine wave and the negative DC pulses to simulate the falling current. This simulated alternating current runs the motor. The most common method of simulating AC current is called pulse width modulation, or PWM. This technique uses 6 specialized transistors, 3 connected to the positive terminal of the DC bridge, and 3 connected to its negative terminal. The inverter's built-in microprocessor rapidly switches these transistors on and off in a particular sequence that generates pulses of rising and falling current. This pulsing current creates positive and negative magnetic fields that seem to revolve through the stator. By controlling when the transistors in the inverter section switch on and off, the microprocessor can vary both the frequency and the voltage the motor receives. Understanding how an inverter controls the frequency and voltage going to a motor makes troubleshooting a malfunctioning system much easier. When you're troubleshooting, keep in mind that you can usually use the inverter itself to help you locate the source of the problem. Many inverters can display fault codes, which tell you a lot about what's wrong. For example, most inverters include codes to indicate when some part of the inverter itself is malfunctioning. This code indicates an error in the onboard microprocessor that runs the inverter. This inverter displays one code to indicate that the input voltage was too low. It displays a different code if the motor has shorted out, and still another if the motor overloaded while it was running. And another code indicates when electrical interference may be garbling input signals from field devices such as limit switches or photosensors. If you're not familiar with what the fault codes mean on the inverters in your facility, refer to the operator's manual provided by the manufacturer. Now let's take a look at some of the common problems that occur in motor control systems using inverters. The AC supply in nearly all industrial locations is subject to voltage irregularities. While some variation can usually be tolerated, irregularities that exceed the design specifications of the inverter may interfere with normal operation. When voltages are higher than normal, rectifiers in the converter section and capacitors in the DC filter section will burn out quickly. High voltages will also cause other components in the inverter to generate excessive heat and become damaged. Even though inverters have cooling fins and sometimes fans to help dissipate heat during normal operation, they may not be able to dissipate the additional heat caused when voltages are above the design specifications. Sometimes industrial supply voltages are neither significantly low nor high, but they are unbalanced. In other words, voltages in the three phases are not equal. For example, the voltage in one phase may be 230, one might be 235, and the third one might be 240. In general, the difference between the lowest and highest voltage should be less than 4% of the lowest voltage. The inverter may be damaged if it is operated on unbalanced voltages. Industrial electrical service is also often subject to power dips and interruptions. These brownouts and outages may cause an inverter to trip out. However, the motor may exhibit only minor dips in torque and speed because many inverters retain sufficient power in their capacitors to allow nearly normal operation for up to half a second. In addition, some inverters can be programmed to automatically restart a motor on the fly, that is, while it is still coasting. Sometimes motors short out more frequently when used in inverter-based systems. This is especially true when standard fan-cooled motors are operated by an inverter at less than rated speeds. The ability of a fan to remove heat from the motor is dramatically reduced as the motor slows down. Yet the motor may still be producing full torque. This can cause the motor windings to overheat rapidly, and if that occurs often enough, the motor will short out. To avoid damaging the motor, voltage and frequency should be changed simultaneously. Most inverters have a variety of volts to hertz ratios which may be set to match the application. If the volts to hertz ratio does not match the motor to the application, the motor may overheat from using too high a voltage at too low a frequency. Another problem you might encounter is excessive vibration in the motor and load. This is usually the result of mechanical resonances. These vibrations often occur when a standard induction motor is operated at low speeds. If the vibration source cannot be eliminated, the inverter can usually be programmed to skip speeds at which the resonance occurs. Sometimes the size of the load may be a source of problems. When very heavy loads must be started or accelerated, most inverters can be programmed to provide a torque boost, a surge of voltage that momentarily increases torque. However, these boosts generate excess heat. To avoid damaging the motor, torque boosts should not be used routinely unless some provision has been made for removing the excess heat from the motor. Loads may also be a source of problems when inverters provide braking. After the inverter cuts power to the stator, the rotor continues to turn because of the momentum of the load. With no current being applied to the stator, the turning rotor acts as a generator, regenerating current that is fed back to the capacitors in the inverter. This drains off the energy of the turning rotor, stopping it quickly. If the capacitors cannot absorb all the energy of the rotor, the inverter will switch a resistor into the circuit to help dissipate the energy. When the load is very large, external resistors may be used to boost the braking capacity even more. However, if the load is too great, or if it is braked too frequently, the inverter may trip out to protect the capacitors and the resistors from damage. When this happens, the braking effect is lost, and the motor simply coasts to a stop. Some controllers provide DC injection braking for the motor. In this braking method, straight DC current is applied to the stator when the motor has nearly stopped. This changes the stator into a stable electromagnet, which locks onto fields in the still turning rotor, bringing it to a halt and holding it firmly in place. In order to perform its job correctly, an inverter-based system must have reliable feedback from field devices. This means that every limit switch, sensor, encoder, or other device in the system must be working correctly and transmitting accurate signals. Each device must be correctly mounted, clean, and undamaged. Every connection must be tight, and every wire must be properly grounded and shielded. The system should include surge suppressors, and power and control wiring should be run in separate conduits. Other problems in inverter-based motor control systems may occur inside the inverter itself. As we've said, most internal faults will show up as error codes. But if the inverter is not indicating an internal fault of some kind, or if the inverter shows an error code and you cannot find anything wrong with the system, you should check the inverter's settings to make sure they're correct before considering repairing or replacing the inverter. These settings are usually programmed into the inverter when it is installed. However, if the application has changed very recently, the inverter may not have been reprogrammed and tested adequately for the new application, or someone may have made unauthorized changes in the programming. When an inverter has developed an internal problem, it will have to be repaired or replaced. If you do have to physically remove an inverter, the first step is to perform a proper lockout, including the control of all stored or secondary energy. With an inverter, this means making certain that the internal capacitors are discharged correctly and completely. Some inverters have neon lamps to monitor the dissipation of the charge on the capacitors. Still, it's never a good idea to trust a lamp completely. Before working on an inverter, read and follow the manufacturer's directions for the correct method of discharging all stored energy. Then, use a DC voltmeter to make sure the energy has been discharged. If the inverter must be replaced, be sure each wire is identified and labeled before you remove it from the terminal strip. Then, when installing the replacement, make sure you fasten the correct wires to the correct terminals on the terminal strip. Be especially careful with the incoming AC lines. If you mistakenly wire three-phase power to the motor terminals, the inverter will be severely damaged when you apply power. In most instances, if an inverter needs to be repaired, it will be returned to the manufacturer or to an authorized repair facility. Complete, accurate troubleshooting of an inverter requires a trained, qualified person and sophisticated tools. Do not attempt any repairs unless you have been properly trained. Improper disassembly may damage inverter components, and improper reassembly could seriously damage the inverter or the system and may cause personal injury when power is applied. In this program, we've discussed what AC inverters are used for and how they operate. We've also provided some guidelines to help you troubleshoot problems if they occur. Now you're ready to take a close look at the particular system you'll be working with. Before you can effectively maintain and troubleshoot any system, you must understand its operation thoroughly enough to know what it should be doing. Then if something does go wrong, you'll be able to identify the source of the problem and take the steps necessary to get the system back online quickly.